Let's consider sinusoidal wave. We're considering sinusoidal wave because it's the simplest example of a periodic wave. So, and suppose that this wave is traveling to the right with a certain velocity v. Then when it travels, it most probably will take a form at a certain time past. It will just look like this yellow line, for example. It will move a little bit further. But our goal here is to describe this wave. I'm gonna clean this yellow line or erase this yellow line so we can really focus on the wave itself. And then we can describe it mathematically. Now, before I go ahead and describe this mathematically, I am assuming that you know what is a wavelength, lambda, what is the period of the wave, what is the frequency of the wave, and the amplitude of the wave. If you didn't have a chance to learn about this, just pause this video here and then go read your book and then come back to this. Now, I said this is a sinusoidal wave, so sine and cosine are kind of the same functions. It just depends for a traveling wave. It depends where the time you take equals 0. It's either a sine function or a cosine function. So it's the form of it. It's called sinusoidal wave. So let's suppose that let's be consistent with our picture and say that we represent our wave function y x at time equals 0 should equal a cosine some kind of constant times x, where a is the amplitude of the wave and then lowercase a is a constant to be determined. Now, so first of all, let's try to see how we can determine the a. So for that, I am going to look at points where the value of y equals 0. So one is in here and another one is in here. Maybe I only need one. So this is 0. This is pi over 2. Right here we have pi. We have 3 pi over 2 here and then 2 pi in here. So as we can see, the value of y equals 0 when x equals pi over 2. So therefore I could say y at pi over 2, which is, you know, I don't want to write pi over 2, but what I want to do, I want to write its wavelength. So that would be at pi over 2, the wavelength is actually lambda over 4. And here we have half a lambda. Here we have 3 lambda over 2. And here we have just one full lambda. Okay, so one full wavelength. So then I would say at time equals 0, when x equals lambda over 4, time equals 0, a cosine a lambda over 4 should equal 0. So from here, this is only possible when your cosine a lambda over 4 equals 0, which means a lambda over 4 equals pi over 2. Then from here, I can solve for a to be 4 pi over 2 lambda, which equals 2 pi over lambda. Now I can represent the general form of my wave function yx0 at time equals 0 equals a cosine 2 pi over lambda x 2 pi, I'm sorry, this is multiplied x, and that would be it. So now let's remember our discussion of pulse. If the wave moves to the right during the period of time t, then in general case we could say yx at time t equals a cosine. So we would have 2 pi lambda times x minus vt. If it is moving with the, so where we can say v equals, we can find a v equals delta x over delta t, and then well, if we consider the delta Lx is the whole wavelength, and then whole wavelength takes a one period to pass. So let's continue on by substituting our velocity by lambda over t, or the speed. Then I would get a cosine 2 pi over lambda x minus lambda over t times t. Okay, move on and then simplify a little bit more. So I have a cosine. I'm gonna have distribute 1 over lambda into the small parentheses. I would have 2 pi x over lambda minus t over the period t. Okay, so first of all, this form actually shows the periodic nature of the wave. Now let's express the wave function in more convenient wave. So let me write it in here, periodic nature of the wave. Now let's represent this in a little bit more convenient way. So I can write y xt equals a cosine. So I'm going to write 2 pi over lambda x minus 2 pi over t. Okay, so why is this more convenient? So I'm gonna name this guy right here as a k, and this is known called angular wave number. Angular wave number. The 2 pi over t is angular frequency. We already know that from our previous studies in physics, and equals 2 pi f. So angular frequency. Now finally I can represent the new form of wave function yxt equals a cosine kx minus omega t. So this is a more convenient way of representing the sinusoidal wave. Now let's do a little bit side work on discussing the angular wave number, angular frequency, and the wave speed with the wave characteristics. It might be useful for later. So I'm going to let's start from the point where we have v. Let me see. V equals lambda over T, which is right from here. I already explained that to you. And so we defined omega to be 2 pi over T. From here follows that period should equal 2 pi over omega. So from the other hand, I have the k that equals 2 pi over lambda, and from here it follows that lambda equals 2 pi over k. So if I plug these two into the equations, the top equation, so this one in here, and plug this guy right here, then I would have V equals 2 pi over k divided by 2 pi over omega, which gives me an V equals omega over k. Something that you wanna you want to, it's a useful equation that you wanna have it in hand. So if I summarize everything together, I could say I could write V equals omega over k, V equals lambda over period, and V equals lambda times frequency. This is something that you want to write somewhere in the hand and use